The function yx satisfies the differential equation as x into dy by dx is equal to y into ln of y minus ln of x plus 1 with the initial condition that y at 1 is 3. Then what will be the value of y at 3? Here the given differential equation can be written as x into dy by dx minus y into ln of this y is equal to minus y into ln of x plus this y. This is our given differential equation. Now this equation cannot be reduced in any type of the differential equation, and now we divide each term of this given differential equation by a factor this x into y. Now dividing this differential equation by a factor x into y in each term, then we obtain that 1 by y into this dy by dx minus 1 by x into ln of y is equal to minus 1 by x into ln of x plus 1 by x. This is equation number 2. Now to solve this equation, we substitute this as a z factor, means this z is equal to ln of y, and then from here we can write it as this dz by this dx can be written as 1 by y into this dy by dx, which is of course the first term. The first term is replaced by this dz by dx, and now minus 1 by x, and this ln y is equal to z, which is equal to then this minus 1 by x into this ln of x plus 1 by x. This is equation number 3. Now this equation number 3 is the linear differential equation of the first order, where p is equal to minus 1 by x and the q is this right hand term which is a function of x. Now then the integrating factor of this linear differential equation is obtained, that e to the power p into dx integral, and this can be written as e to the power integral of this minus 1 by x into dx, which can be written as e to the power minus ln x, which can be again written as x to the power minus 1, and that is 1 by x. Now on multiplying this equation 3 with this factor 1 by x, we got that this 1 by x into dz by dx minus 1 by x square into z is equal to minus 1 by x square into ln of x plus 1 by x square. This is equation number 4. Now this equation can be simplified in the left hand side by taking the derivative of this z by x, as the derivative of this z by x term can be written as 1 by x into dz by dx minus 1 by x square into z. Here this term can be written as d by this dx, this is the derivative of this z by x term, which is equal to minus 1 by x square into ln of x plus 1 by x square. Now on integrating the both sides, we can write it as this z by x is equal to the integration of this minus 1 by x square into ln x into dx plus the second term integration, that is equal to 1 by x square into dx plus a integration constant, say this c. Now the integration of this first term on the right hand side can be written as by taking this negative sign outside from the bracket, and this integration is written as minus ln x by x plus the integration of this this 1 by x square into dx, this is equal to 1 by x square into this dx here, and this is the first term, and from the second term can be written as this 1 by x square integral with dx plus this c. Now this equation is simplified as this can be simplified as this z by x term is equal to this minus and minus become plus, that is equal to this ln x divided by x, and this integral become the negative by multiplying this negative outside from this bracket, and this next term is the integral of 1 by x square into dx, and of course this plus c here. This negative term is cancelled out with this positive term, and from here we can write it as this ln by x plus c. Now this multiplying this variable z to the each term, then we obtain from here that z is equal to ln of x plus c into x. This is the equation number say 5, and this is our value of z. But this is the solution in term of z, but we have substituted as z is equal to ln of y. Therefore y is equal to e to the power z. We have substituted again here. Then we take the exponential of both this term, then we can write it as this exponential of this e to the power z is equal to exponential of this whole term, and this can be written as ln of x plus this c into x, which can be simplified that this x into e to the power this c into x. This is the value of this e to the power z, and this okay. Now from here we can write it as this y is equal to x into e to the power c into x. Now applying the boundary condition, the initial condition that y is equal to 3 at x is equal to 1, then this y is equal to 1 at this x is equal to 3, then from here we can write it at e to the power 3 into c, and this at x is equal to 1, sorry, this x is equal to 1, and from here we can write it as this is of course 3, y is equal to 3 at x is equal to 1. Then from here we can write it as like this is 1, not this 3. Then from here we can write it as e to the power c is equal to 3, and from here we can write it as c is equal to ln of 3. Now substituting this value of c in this given solution, this given solution is the equation number 6. Then by substituting c in equation number 6 we obtain, then we can write in our solution that y is equal to x into e to the power this ln of 3 into x. This can be written as this x into e to the power x into ln of 3. Now taking the power of power in this x in the power of this 3, we can write it as x into e to the power ln of 3 to the power x, and from here we can write it as x into 3 to the power x. That is our final solution, and hence y is equal to x into 3 to the power x is our final solution. Say this is equation number 7. Now we have to find the value of this y at x is equal to 3. Then we substitute x is equal to 3 in the equation 7, and then we can write it as this, and this become as 3 into 3 to the power 3 is 27, and this is equal to 81, and we can plot the given solution of this differential equation is like that. Here x, and here this our y, and this is exponentially rise, and here at this particular value of say this x is equal to 3, this equation obtain the value, and here this is the 81. Like this we can plot the solution of this differential equation. Write down xt, where xt is the solution of the following differential equation, and the differential equation is given by d by dt plus 2 into d by dt plus 1 into x is equal to 1, with the boundary condition that dx by dt at t is equal to 0 is 0, and x at t is equal to 0 is minus half. Here the differential equation is given in this form, in the form of this d by dt operator, and we can write it as that d by dt plus 2 and into d by dt plus 1 into x is equal to 1. Now on solving this operator term, we can obtain that this d by dt into this second term, that is equal to d by dt plus 1 plus 2 times of this d by dt plus 1, and this, of course, this is all multiplied by this x is equal to 1. Now on solving this, we can write it as this is d2 by dt square plus, and this d by dt of this one becomes 0. Now the second term is expanded like this 2 times of this d by dt, and this 2 is multiplied with this 1, and of course here x and then equal to 0. Now this equation can be written in the differential operator d form by substituting this d by dt square is equal to d square, and this d by dt is equivalent to the operator d. Then we can write it as this d square plus 2 times d plus 2 into x is equal to 1. Now this is say the equation number 1, and from this equation number 1 we can obtain the auxiliary equation by substituting this d square is equal to m square and d is equal to m. Then the auxiliary equation is obtained that m square plus 2m plus 2 is equal to 0. From here we can obtain the root of this auxiliary equation is m is equal to minus 1 into plus minus iota. Here the root are the complex root, therefore the solution of this given differential equation is written as x, which is a function of t, is equal to this can be written as e to the power minus 1, that is the real part of the root, into x, and here say this c1 into cos of this coefficient of imaginary part, that is equal to 1. Then here we can write it as only here this t, and of course this is also a variable t here, and plus this c2 into sine of t here. Like now this is our solution. Say this is equation number 2. Now substituting the initial boundary condition that dx by dt at t is equal to 0 and this xt at t is equal to 0 is minus half. Substituting this second condition that xt at 0 is minus half, then we can write it as this minus half is equal to e to the power minus t at t is 0, therefore this is 0 here, and c1 into cos of t become 1, and this plus c2 into sine of t, the sine of t becomes 0, therefore here 0, and from here we obtain that this c1 is equal to minus half. This is say equation number 3. Now taking the derivative of this xt from the equation 2 by substituting the value of c1, we can write it as xt is equal to e to the power minus t into the value of c1, that is equal to minus half into cos of t plus c2 into sine of t here. Now taking the derivative of this this equation is say the 4, and taking the derivative of the fourth, we can write it as x dash t is equal to here the e to the power minus t, it's taking the same, and then derivative of this term, that is equal to minus 1 by 2 into this sine into t, and of course with the negative sign this minus sign become the plus sign, and then this derivative of this second term is plus c2 into cos of t here, and the second term is now written as same, and the derivative of this first term become as minus e to the power t minus t into this second term as same as before, this is cos t by 2 with the minus sign plus c2 into sine of t. Now substituting the value of t is equal to 0 in this equation number, this is equation number 5, then we obtain that. Now this equation with the derivative I have written here in the simplified version. Now by taking by putting the value of t is equal to 0 then this x dash become 0, and we can write it as this x dash is equal to 0, then this exponential term become 1 at t is equal to 0, and this term become 0 due to this sin t, plus this c2 and this cos t become 1, then minus sin, and this exponential term become again 1 due to this t is equal to 0, and this term with the c2 coefficient become 0 due to this sign, and this term become minus 1 by 2. And from here we can obtain that 0 is equal to c2 minus, and this minus become as a plus is equal that is equal to plus 1 by 2, and from here we can write it as that c2 is equal to minus 1 by 2. And we have also obtained that this c1 is also equal to minus 1 by 2. Then the final solution of this differential equation can be written as that xt is equal to e to the power minus t, and this c1 into cos of t, and of course c1 and c2 are equal, therefore by taking common we can write it as minus sign, and this is by 2, and here cos of t and plus c2 time of sin t, and by as the c2 is taking outside from the bracket, and here only sin t is remaining here. This is our final solution, and this solution can be plotted with the graph by taking, this is say our t axis, and starting from this 0, and this is our this xt solution. This solution is starting from the 0, it goes to the rise as like this, then is down, and then it approaches to this a constant value, and this constant value that it approaches this is equal to this is equal to 0, that is given as this xt is 0 for the large value of this time. If yx satisfy the differential equation y double dash minus 4 times y dash plus 4y is equal to 0 with the boundary condition that y is 1 at x is equal to 0 and y dash at x is equal to 0 is 0, then obtain the value of y at x is equal to minus half. Here the given differential equation is given as this y double dash minus 4 times y dash plus 4 times y is equal to 0. This is say equation number 1. Now by substituting this y double dash is equal to d square, and this y dash is equivalent to this d, then we can write this differential equation into this differential operator form like this. This is the differential equation in differential operator d form. Now from here we can obtain the auxiliary equation by substituting d is equal to m, then equating to 0, then we can write it as this m square minus 4 times m plus 4 is equal to 0, and from here we can obtain the value of m, that is equal to 2 and 2, which are the repeated value. Therefore the solution of this differential equation can be written as y is equal to c1 plus some c2 into x into e to the power 2x. Here this is our solution or the general solution of this given differential equation. Now here there are the two arbitrary constants c1 and c2. We can obtain the value of c1 and c2 by using the boundary condition, and the first boundary condition is that this at x is equal to 0, this y become as 1, then from 3 we can write it as 1 is equal to this c1 plus c2 into x, and that is 0, and into e to the power 2x, that is equal to again this exponential factor become 1, and from here we can write it as this c1 is equal to 1. Now substituting the value of this arbitrary constant c1 in the equation 3, then we obtain that y is equal to this 1 plus c2 into x into e to the power 2x, which can be again simplified as e to the power 2x plus c2 into x into e to the power 2x. This is say equation number 4, and which contain an arbitrary constant c2, which can be calculated using the second boundary condition that the y dash at x is equal to 0 is 0. For this we have need this y dash, and y dash is obtained from here that this 2 times e to the power 2x plus this c2 and this x into 2 times e to the power 2x plus this e to the power 2x into this 1, and this is the derivative of this y. Now substituting the condition that this y dash is 0 at x is equal to 0, then this becomes 2 into 1 plus here c2, and this term becomes 0 due to presence of this x, and plus this term become as this 1, and from here we can write that this c2 is equal to minus 2. Then by putting this value of c2 in this equation number 4, then we obtain our solution is y is equal to e to the power 2x minus this 2 times of x into e to the power 2x, which can be compact in this term like e to the power 2x into 1 minus 2 into x into e to the power 2x. This is our final solution, say equation number 5. Now we have obtained the value of this y at x is equal to minus half. Then we substitute x is equal to minus half in the above equation, and then we can write it as e to the power 2 into minus half here. Now on solving here, we can write it as 1 minus into minus become plus, therefore this 1 plus 1 become 2 into this exponential factor become as e to the power minus 1, and from here we can write it as this is 2 by e, and hence the value of this y at minus half, this become 2 by e, which is correspond to the option A, and hence option A is the correct option. Also, the solution of this differential equation can be plotted like this. This is our x-axis, say this 0, and this is our y-axis. Then at a very less value of the x, means the negative value of the x, this is solution is almost going to here, and then it is slightly increasing, and this is approaching to 1 here. Here this is 1, this y is equal to 1, and this again going down like this, and this cutting point at x is equal to x is equal to become is 1 by 2 here, this 1 by 2 here. This is the plot of this solution of this differential equation. Consider the two equations. The first one is this x square by 3 plus y square by 2 is equal to 1. Of course, this equation is the equation of ellipse. And the second one is the x cube minus y is equal to 1. Then how many simultaneously real solution does this pair of the equation have? Here this first equation is given as x square by 3 plus y square by 2 is equal to 1. And this equation can be rewritten as this 2x square plus 3y square is equal to 6. This is say our equation number 1. Now the equation number 2 is given as this x cube minus y is equal to 1, and from this equation number 2 we can obtain this y is equal to x cube minus 1. This is the equation number 2. Now substituting the value of y from this equation 2 to this equation 1, then we can write it as 2 times x square plus 3 times y square, and y is equal to x cube minus 1, therefore its square, and is equal to 6. Now on simplifying this equation, we can write it as this 2x square plus this 3 times x to the power 6 minus this 6 times x cube, and this plus 1 will multiply with this 3, this is 3, and is equal to this 6. On simplifying this, we can write it as this 3 x to the power 6 minus 6x cube, this plus 2x square minus this 3 is equal to 0. This is our final equation. Now from this equation we applied the discard rule of change in sign. For the positive root of this equation 3, we can write as this positive root. Positive roots are obtained by observing the change in sign in this equation, and this equation is written as this 3x square minus 6x cube, this 3x power to the 6, and this 6x cube plus 2x square minus 3 is equal to 0. in this equation we can observe here this is the positive sign and this positive to this negative is the one change in sign, and this negative to again this positive, this is the second change in sign, and this positive to this negative, this is again once again it is change in sign, and hence here are the three change in sign. Therefore that implies there is the maximum number of positive roots are the threes. There are the three maximum positive roots are possible. Now if we substitute this x is equal to minus x, that means our negative root, for this negative root we can substitute as x is replaced by this minus x, then our equation 3 become as, by substituting x is equal to minus x, this first term is as it is 3 into x to the power 6, and this second term become as positive, this is 6x cube, and this again third term as the even term, therefore the same as it, and this fourth term is constant which is equal to 0 now. And in this equation we observe here this is not change in sign, and from here to here not change in sign, but from here to here is a change in sign in 1. Therefore here the maximum one negative root are here, means one negative root real root are here and three positive root are here, and total number of the 4, that is the 3 positive and plus 1 negative, and the maximum 4 real root are possible, real roots are possible, and hence there are the 4 real root are possible. The differential equation x into dy by dx minus xy is equal to exponential of x, where y is equal to e square at x is equal to 1. Then the solution y is, here the differential equation given as x into dy by dx minus x into y is equal to e to the power x. Now dividing this equation by x in each term, then we obtain that this dy by dx minus y is equal to e to the power x divided by x. On comparing this equation with the general first order linear differential equation, we can write it as this p is equal to minus 1 and this q is equal to e to the power x by x. Now the integrating factor for this differential equation is given as e to the power integration of p into dx, and here p is minus 1, therefore this become as minus into dx. On integrating this we can write it as this e to the power minus x. This is the integrating factor for this given differential equation. Now the solution for this differential equation can be written as y into integrating factor is equal to integration of this integrating factor into q into dx plus some arbitrary constant c. For here we can write it as y into integrating factor, that is e to the power minus x, is equal to integration of this integrating factor e to the power minus x into q, and q is equal to e to the power x by x into dx and plus this c. Now on integrating this e to the power minus x is cancelled with this e to the power x, and here this integration is dx by x plus c, and on integrating this we can write it as this is ln of x plus c, which is equal to y into e to the power minus x. Now to obtain the value of this arbitrary constant c, we use this boundary condition given that at x is equal to 1, this y become as e square. Now substituting y is equal to e square and x is equal to 1, that e square into e to the power minus 1 is equal to ln of 1 plus c. This ln of 1 is 0, and from here we obtain this is equal to e to the power 1 is equal to c, that means this c is equal to e. Now substituting this value of arbitrary constant in this solution. Here we can write it as this y into e to the power minus x is equal to ln of x and plus this value of arbitrary constant that is equal to e. Now from here we can write it as y is equal to ln of x plus e divided by this e to the power minus x. This can be again written as y is equal to e to the power x into ln of x plus e to the power x into e, and this can be finally written as e to the power x into ln of x plus e to the power x plus 1. That is the final solution, which is correspond to the option D here, and hence option D is the correct option. The solution of the differential equation given by dy by dx is equal to 1 plus y by x minus y square by x square for x greater than 0 with the boundary condition that y is 0 at x is equal to 1 is given by this yx is equal to. Here the given differential equation is written as dy by dx is equal to 1 plus y by x minus y square by x square. From here we can notice that in this given differential equation in each term the power of x and y are the same. Therefore this each term of this differential equation is homogeneous, and this can be reduced to the general homogeneous equation by substituting y is equal to v into x. Then this dy by dx can be written as v plus x into dv by dx. Now substituting the value of y and dy by dx in this given equation 1, and we can write as v plus x into dv by dx is equal to 1 plus, by putting the value of y here, y is equal to vx, then we write it as vx by x minus this v square x square by x square, and on solving this equation we can write it as this x is cancelled with this x, and of course this x square is this x square, then this v is cancelled with this v, and we can write it as x into dv by dx is equal to 1 minus v square. Now this equation can be easily solved by using the variable separation technique, and we can write it as this dv by 1 minus v square is equal to this dx by x. Now this now integrating on both sides, and for this integration we use here the partial fraction, and for using the partial fraction we can write it as a divided by the first factor of this denominator, that is 1 minus v, plus some another constant b divided by the second factor of this denominator, that is equal to 1 plus v, and this can be written as 1 by v square. Now from here we have to obtain the value of a and b. Now multiplying on both sides by 1 minus v square and comparing the coefficient of the constant term as well as the v term and v square term, we can obtain from here a is equal to b is equal to 1 by 2, and hence this equation, this is say equation number 2, can be written again as this dv divided by 1 minus v, of course here 1 by 2 factor also present, and the next term that is equal to plus the value of b is equal to 1 by 2, and this dv divided by 1 plus v, and this is equal to this dx by x here. Now integrating now on both sides, then we can write it as the integration of this term can be written as minus 1 by 2 into ln into 1 minus v. This minus sign is due to this this minus v present here. Now again this integrating this second term, we can write it as 1 by 2 into ln into 1 plus v, which is equal to, again this integration become as ln of x, and now adding a constant term that is equal to ln into c. Now on combining all these logarithmic term on the left hand side as well as in right hand side, we can write it as on the left hand side that ln of 1 plus v divided by 1 minus v, and of course from here we take this power by 1 by 2 as the outside, and we can take it as the power here 1 by 2, and which is equal to ln of x into c here. And now we can solve here by taking the exponential on both sides. Then we can write it as 1 plus v divided by 1 minus v to the power 1 by 2 is equal to this x into c. Now this is say equation number 3. On squaring both sides, we can write it as 1 plus v divided by 1 minus v is equal to x square into c square, and c square again can be replaced by another constant, say capital C. Then this can be written as x square into this c here. Now from here we have to obtain the final solution in term of y and x. Therefore we substitute from the initial substitution that y is equal to vx, then from here v is equal to y by x, and then the solution become as 1 plus y by x divided by 1 minus y by x is equal to c into x square. Now substituting the first the given boundary condition that x is equal to 1, then this y is equal to 0. Substituting x is equal to 1 and y is equal to 0, we can write it as 1 plus 0 divided by 1 minus 0 is equal to c. That gives us this c is equal to 1, and from here we can write it as this x square is equal to 1 plus y by x, means this x plus y by x, and this can be written as x minus y by x, which x in the denominator term is also cancelled with this numerator term, and this is the value of x plus y and x minus y. From here we can calculate as this y is equal to this x into x square minus 1 divided by 1 plus x square, which is correspond to the option A, and hence option A is the correct option. Consider the improper differential that is given by ds is equal to 1 plus y square into dx plus xy into dy. Then what is the integrating factor for this improper differential? Here we know that the improper differential equation is given by this m dx plus n dy, and on comparing with this we obtain that m is equal to 1 plus y square and n is equal to x into y. Now taking the partial derivative of m with y, we can write it as curly m by curly y is equal to 2y, and taking the partial derivative of n with x, then we can write it as equal to x. Now we can take this curly m by curly y minus curly n by curly x divided by this n, which is, say, this is a function, say function of x fx, which can be obtained as by substituting the value of curly m by curly y, that is 2y, minus curly n by curly x, that is y, divided by x into y, and on solving this, from here we obtain this fx is equal to 1 by x. Now to obtain the integrating factor, we can write as integrating factor is equal to e to the power integration of this fx into dx. Now substituting the value of fx, we can write it as 1 by x into dx and its integration. Now this can be written as e to the power ln of x, and from here we can write it as this is equal to x, and hence from here we can write it as the integrating factor is x, and of course any constant multiplication of this integrating factor is again an integrating factor. Therefore this minus x also an integrating factor for the given improper differential, and hence option A is the correct option. A differentiable function f(x) obeys x into integral of 0 to x of fy divided by y square into dy is equal to fx. If this f at x is equal to 1 is 1, then it follows that f at x is equal to 2 is. Here the given function can be written as this integral from 0 to x of this function f of y divided by y square into this dy is equal to fx divided by x. This is equation number 1. Now here we differentiate this function with respect to x on both sides, and for that we use this Leibniz rule of differentiation, and this Leibniz rule of differentiation is defined as if suppose we have a function y is equal to the integral from this phi x to some say this psi x of a function f which is a function of x and t into this dt, then the differentiation of this function can be defined by using this Leibniz rule, that is equal to dy by this dx is equal to the integral of the function from this lower limit phi x to this upper limit psi x of the function of df divided by dx into dt plus the value of the function at x is equal to x and t is equal to, that is upper limit of this say the psi x into the derivative of this upper limit psi dash x minus f into x into the lower limit value that is equal to 5x in replaced by this t and the derivative of this lower limit phi dash x. Now using this Leibniz rule in our problem that is defined by the equation number 1, then we can write it as first we put it like this by the derivative that fx divided by this x square into 1. This is obtained by substituting that this x is equal to this y this y is equal to x here, and we got. Now by substituting the lower limit here, we can write it as this f at 0 divided by x0 into this derivative into 0. This term becomes as the 0 as a whole. Now on the right hand side, if we differentiate this can be written as this fx divided by minus x 1 by x square and this plus f dash x divided by this x. Say this is equation number 3, which is obtained by the differentiation of 1 by using this Leibniz rule defined here. Now on simplifying this, we can write it as this 2 times of this fx divided by this x square is equal to f dash x divided by x, and again we can further simplify it as this can be written as this 2 divided by x is equal to this f dash x divided by this function f of x. This is equation number 4. Now on integrating on both sides, from here we can write it as this 2 times ln of x is equal to this log of this means this ln of this function fx here, and also we add here a arbitrary constant, say this ln of a, and on combining this we can write it as this can be written as this x square is equal to and from here we can write it as a into this fx function here. Now to obtain the value of this arbitrary constant a, we use this given condition that this function f at 1 is 1, therefore this x is equal to 1, and here this a into this function become 1, and from here we obtain that this a is equal to 1. Then our function can be defined by using the value of arbitrary constant a. Then our function can be written as this x square is equal to this function f of x. Now we have find the value of our function at x is equal to 2. Then we can obtain that this function f of 2 is equal to x square, that means this 2 square, which is become 4, which is correspond to the option A, and hence A option is the correct option.